Welcome back. So let us get on more problems, worked examples. So we have yet another problem having to do, of course, with Leibniz formula. So let's see this problem. It says that suppose y satisfies this relation, the squared y over the x squared plus x squared y equals sine x at x equals 0. Show that the n plus 2 y plus n into n minus 1, the n minus 2 y equals 0 if n is even, and equals plus or minus 1 if n is odd. Alright, so we have yet another problem where we have to apply, or we need to apply. I need to verify this question is correctly written. X square y dx squared plus x squared y equals sine x at x equals to 0. Show that the n plus 2y into n minus 1 to n minus 2y. Alright, so we know that we will have to apply Leibniz theorem. This is quite similar to some of the problems we solved previously. We can easily identify that this is the second derivative of y. This is zeroth derivative of y, and for this case we don't have it to be equal to 0. We don't have equal to 0 on the other end, so there's clearly no need to actually move this to the other side. For instance, we can just deal with it the way it is here. We can take the nth derivative. Of course, we still need to take the nth derivative. This is basically the n plus 2 derivative, so that means that if we have the second derivative already, for us to get the n plus 2 derivative, we should take the nth derivative of this expression. So we go ahead and do that now and see what it gives us. So given that the squared y, the x squared plus x squared y equals sine x. We can write this using that y sub n notation. We can write this as, this implies that y sub 2 plus x squared y equals sine x. So then if we take the nth derivative of both sides, so the n of y sub 2 plus x squared y will be equal to the n of sine x. So for us to proceed, why are we doing this? Because of this. This means y sub n plus 2. Okay, this is n plus 2 derivative. So to arrive at something similar to this, we know we just have to take the nth derivative of this equation. Okay, so going further now, when we open up this bracket, this is going to be the n of y sub 2, then plus the n of x squared y equal to the n of sine x. So we come back to get the n of sine x. So for in all of this, we don't need Leibniz formula to obtain this derivative. We need Leibniz formula for this because, of course, y is going to be some function of x, and this is some function of x also. So we'll come back to that. But for this, we can easily identify this as y sub n plus 2 because that's the nth derivative of the second derivative. So we'll just add them up. So we have this to be plus the n of x squared y. Again, we'll come back to this, equals the n of sine x. Again, we'll come back to this as well. So this is our equation A right here. So let's obtain these derivatives one after the other. We don't need to apply the Leibniz formula for this case, but we can easily find out. Um, so we can say, let's say, for instance, I don't want to use U, I don't want to use V, because we're going to use that for this case. When we want to use the Leibniz formula, I mean, that's just what we're already familiar with. So to avoid complicating the presentation, so let's use W, so omega if you like, be equal to sine x. Then the the W, derivative of sine x, is cos x. And of course, this is the same thing as having sine x plus pi over 2. So we've talked about this before that okay, we did for cos x before. Okay, it happens that sine x also has a derivative to actually be similar to the expression for the n of cos theta cos x. So basically, the idea is that if we have cos x, we know it's the same thing as sine 90 minus x, that's pi over 2 minus x. And we know that for the second quadrant, on the second quadrant, we had this sine 180 degrees minus theta. That's sine pi minus x will be equal to sine x. Okay, so basically, if we have pi minus whatever we have here, then it will be equal to whatever it is we add here. So we can write then that cos x will be equal to sine of, instead of this, we can write the pi minus what we have there. So pi minus pi over 2, then minus x, that will be plus x. So pi minus pi over 2 will give us pi over 2. So basically, this is the same thing as sine of x plus pi over 2. So that's how we came about this. And if we differentiate further, the square omega with derivative of course, and that will give us minus sine x, derivative of cos x is minus sine x, so we can write this as sine of x plus pi, that's 180 degrees plus x. That will be third quadrant, and on the third quadrant we know that our sign is negative there, so basically that captures that for us. And if we go further, the cube omega, and that will be derivative of sine x. Derivative of sine x is cos x, so this is basically going to be minus cos x, and this will be sine of x plus, so we can see this as 2 multiplied by pi over 2. So just to um, move towards that pattern as we proceed, so we can write this as 2 multiplied by pi over 2. That will give us pi, of course. This will be 3 multiplied by pi over 2 also. So this will give us that result that we need for minus cos x. The explanations are similar. We can easily derive that from quadrant of angles. And so it keeps going on like that and like that, and we can easily see that the nth derivative of sine x is going to be equal to sine of x plus n multiplied by pi over 2. So basically that is what we need for this portion. So we'll use that when we get there. So let's add an additional page now. So we have this, we can call this equation star, because we'll come back to substitute it here. So the next thing that we need to deal with is this, for which we have to apply the Leibniz formula. So we now say that to find the n of xy, I mean, that's basically what we have up here. We want to get that derivative now. So to do that, we can say let u be equal to x and v be equal to y. If that is the case, the u, that's the first derivative of this, is 1. The v will be equal to y sub 1, that's the first derivative of y. And the squared u will be equal to derivative of 1, which is 0. The squared v will be equal to y2. And from this we can generalize already that to get the nth derivative of u, it is going to be 0 as long as n is greater than or equal to 2. And let's write this properly. So this is the n u, and this will be generalizing from here. This will be the n v equals y sub n. So basically that's what we have for this expression. So we'll make use of the Leibniz formula now. So we now say that from Leibniz formula. So what happens from here? We know that our dn of uv is meant to be we obtained this already, so I'm just trying to remember that expansion that we already did. This is u the n v plus n into the u the n minus 1 v plus n into n minus 1 over 2 the squared u the n minus 2 v, then plus we can just stop here. We know that from the second term forward it's going to give us 0, so just stop there. And of course we know it continues in that pattern, even though the rest will give us 0. So our u is basically so basically this is implying that our dn of xy, so our u is x and our v is y, so this will be equal to u, our u is x, so we can put that here. This will be x into the n v, so I've seen the n v is y sub n, so this is y sub n plus n multiplying du, so our du is 1, so this is n multiplying 1, then the n minus 1 v, so that will just be replacing n here with n minus 1, that's y sub n minus 1, then plus the next one n into n minus 1 over 2, then the square u obviously here is 0, then multiply by this, that's y into n minus 2, and this will continue like that, but then give us 0 all through. So it's because this is giving us 0 already. So basically, this is going to be x y sub n plus n y sub n minus 1. So we can identify this as our equation star. Okay, we have star up there already, so let's call this star star. Okay, so now we have the expressions we need to simplify our equation A. So we can put all of those things back here to simplify our equation A. So we see that going further now, equations, substituting equation star and star star in equation A, what is going to happen? So we'll get back to equation A. For equation A, we have this expression to be yn plus 2. So just put that in. Yn plus 2 comes first. Yn plus 2. Then we add the derivative of xy. Okay, the nth derivative of x. Sorry. We've been doing something wrong. This is x squared y. This is x squared y. So this is an error here. It's meant to be x squared y. Alright, did I write xy? So it's x squared y. So let's correct that. This is x squared y. Please, let's correct that. X squared y. So this is meant to be x squared. So this will be 2x. Then the next one will be 2. So it is the third one. The cube u will be equal to 0. Alright, so of course this will still be this, but then it will be from 3 upward. Okay, so let's correct that here as well. We know that this shouldn't be 0 yet, so let's put that right here. Let's write out the third term here. You know the third term here is meant to be n into n minus 1 into n minus 2, then divided by 6, then multiplied by the cube u, the n minus 3b, and it continues like that. Okay, We're doing that now because we know that it is until the third derivative that this becomes 0. So just want to put it there. So we know it becomes 0 from this point forward. And so we can correct this as well. Um, so we need to just wipe off everything here. Just and write it from the beginning. So wipe this off. Wipe this off. So this is still this is x squared y. This is the n of x squared y, and this will be equal to u. Okay, so our u is x squared, not x. So that is meant to be x squared multiplied by the n of v, that remains the same, that is y sub n plus n into the u, that's the derivative of this, which is 2x, then multiplied by y into n minus 1 plus n into n minus 1 over 2, the square u, that is 2. We have that up here, the square u is 2. So this is meant to be 2 multiplied by y into n minus 2, then plus, so it's from this point forward that it becomes 0. So this will be n into n minus 1 into n minus 2 divided by 6. Then we have this to be 0. Then multiplying y into n minus 3. Then plus, and so on and so forth. Then plus 0. So this goes to 0 from this point. So we know that this is all we have for this situation. Okay. We can call it equation star just to conserve space, so we don't have to clear the next one. So equation star star. All right, so we can now go ahead and with our substitution, we've corrected that. Okay. Um, so for our substitution into equation A, this is what we need to substitute next, which is what we just corrected now. So we can say that this is going to be plus what we obtained here, which was x squared y sub n, then plus 2nx y sub n minus 1, then this 2 we cancel this 2, then plus n into n minus 1, then y sub n minus 2. So that's everything we have for that. Then we say is equal to from equation A is equal to the nth derivative of sine x. We've seen that the nth derivative of sine x is sine x plus n pi over 2. So we can write that here. So this will be equal to sine x plus n pi over 2. So that is all. That's all we have from this expression. So we're good to go. We now have the relationship between the different terms we have here. But that is not really the issue. We have been asked to show that. So looking at the expression we have here, we have been asked to show that this is going to be equal to this expression at x equal to 0. So if we want to use the terminologies they have used here, or the notations that they have used here, then we know that y sub n plus this expression here is the same thing as what they wrote up there as the n plus 2y. Okay, so this is y sub n, so that could be written as plus x squared the n y. This is 2nx yn plus n minus 1. So this can be written as 2nx into y. Sorry, so we can write that as, just to conform with what we have up there, the n minus 1 y, then plus n into n minus 1, the n minus 2, the n minus 2y is equal to what we have up here, which is sine x plus n pi over 2. So we are good to go, but we have not arrived at our destination yet, because as we can see, for this problem, we were asked to show that this, look at it now, we were asked to show that this expression is equal to 0 or plus or minus 1, depending on whether n is even or odd. But we were told that we should do that at x equal to 0. So we substitute x equal to 0 in the results we just obtained now. So let's get back there and substitute x equal to 0. So it will follow then that therefore at x equal to 0, what's going to happen? Substitute x equal to 0 here. This doesn't have x, so this is just going to be the n plus 2y. So whatever this is at n at x equal to 0, we don't know, so we just leave it like that. Plus this one is x squared, so this will be 0 squared the ny plus 2nx, that will be 0, the n minus 1y plus n into n minus 1, okay, into this doesn't carry x, so this is the n minus 2y equals sine of, this is 0, x is 0, so this is 0 plus n pi over 2. So that's what we have left. This will vanish, this will also vanish. So from here we now have only the n plus 2y plus n into n minus 1, the n minus 2y is equal to sine n pi over 2. So that is that about that. So we now have our expression at x equals to 0. So this is what is going to happen at x equals to 0. So let's see what we have been given. We see that in the given question we have exactly this. Okay, this left hand side is already sorted. It is exactly what we just obtained now. So the only part, well, that we have to now deal with is the right hand side. We know the right hand side currently has sine of n pi over 2. So let's see what will be the values of sine of n pi over 2. Don't forget that n is a natural number, so we can only take on positive integers from 1 upward. That's why we have to just consider what happens to sine of n pi over 2, okay, for positive integers from 1 upward, of course. So this is going to be, let's bring up our calculator and just see that for ourselves. Sine of n pi over 2. Let's see with that, we get sine of, we just want to play around with this and see the behavior of sine of n pi over 2. So this is sine of pi over 2, okay? So let's leave it at that. Sine of pi over 2, that means in this case n is 1. If we put that, we get 1. If we increase the coefficient to 2, so let's keep playing around with this coefficient, so 2 times this, and we get 0. If we change the coefficient to, let's say, 3, let's see what happens. This is going to give us minus 1. If we change the coefficient to, say, 4, let's change this to 4, it will give us 0. So we can see that when it is even, that is when this coefficient is even, that's our n in this case. When n is even, it is giving us 0. So if we check again for another even number, let's say we check for when n equals to 6, for instance, it still gives us 0. So when n is even, this expression will always give us 0. And when n is odd, so we've checked for n equal to 1. Let's check for n equal to 3. It will give us this expression minus 1. Let's check for n equal to 5, the next odd number. It will give us 1. Check for n equal to 7, the next odd number. It gives us minus 1. So we see that when n is odd, this goes this is either giving us minus 1 or 1, and when n is even, it is giving us 0. So basically that is the behavior of this expression, because it can only take in positive integers. It can only take in positive integers, yes, positive whole numbers. So basically we will identify, having identified the behavior of this, we will now conclude that indeed this is the n plus 2y plus n into n minus 1, the n minus 2y equals, so for this function we know that it is going to be 0 when n is even, and this is going to be plus or minus 1 when n is odd. So that is the behavior of this expression. And so that completes our proof. So life can be as easy as that with Leibniz formula. So um, we are done with this Leibniz formula. So basically, the problems you come across having to do with application of Leibniz formula will be when you have a product of two functions, one of them carrying x or some powers of x, that we can easily see that its derivative vanishes, okay, with higher n. Then the other function that we can easily get its own nth derivative in terms of n. So when we have that, we know we can just apply Leibniz formula to it. So if it is not a product of two functions, if it's a singular function carrying x, then we will just differentiate it normally to obtain the nth derivative. That is, observe the pattern if it is not vanishing and obtain a formula for the nth derivative. So if it's a product of two functions, we will have to use Leibniz formula. That is when it is useful. And these are, we have seen different patterns of questions or problems may come across under this topic already. You may have a situation where you are given the function, that's y equal to maybe tan inverse of x, like we saw in the last example, where in that case we had to obtain a relationship like this from the definition of the function itself. We had to look at what's the first derivative, what's the second derivative, what's the relationship between them. Can we get an equation like this? And then we'll now take the nth derivative of that equation to arrive at what they have asked us to show. But this is quite easy because they already gave us the relationship and we just want to show this, so we know to just take the nth derivative of this expression to arrive at a conclusion related to this. Okay, so that is that about that. We'll proceed from here in the next lesson to consider another thing about differentiability. Thank you for watching.